This is Nisarga, currently studying in Sri Venkateshwara College of Engineering, Bengaluru, first year PE. The subject is mathematics and the topic is Markov Analysis. Let us go to the topic, uncovering patterns in stochastic processes. Welcome to this presentation on Markov's analysis, a powerful tool for understanding and predicting the behavior of systems that evolve over time in probabilistic manner. We will explore the fundamentals of Markov's processes, delve into applications across various fields, and discuss the limitations and future directions of this fascinating area of mathematics. Introduction to Markov processes. Defining Markov processes. Markov processes are powerful mathematical models that describe systems evolving probabilistically over time. They are characterized by a fundamental property known as memoryless or Markovian property. This means that the future state of a system depends solely on its present state, with no influence with the past history of the system. This unique feature of Markov processes sets them apart from other stochastic models, as it allows for a simplified analysis and prediction of the system's behavior. Examples of Markov's processes. Markov processes find applications in diverse fields including weather forecasting, financial market analysis, customer behavior modeling, and epidemiological studies. They provide a powerful tool for understanding and predicting the complex systems with inherent uncertainty. Now let us see how Markov's rule is applied in mathematical applications. Markov's rule, also known as Markov's property, is a fundamental concept in probability theory and stochastic processes. It states that the future state of system depends only on the present state and not on the past states. Probability modeling. Markov's rule allows us to model and analyze stochastic processes such as random walks, queuing systems, and population dynamics, where the future state is determined solely by the current state. Optimization problems. Markov's decision processes, which rely on Markov's rule, are used to solve optimization problems in areas like resource allocation, inventory management, and reinforcement learning. Time series analysis. Markov's models such as Markov chains are used to analyze and forecast time series data in fields like finance, economics, and engineering, where the future value depends on the current value. By leveraging Markov's rule, mathematicians and researchers can develop powerful models and algorithms to understand, predict, and optimize complex systems in a wide range of applications. Let us take a simple example of how Markov rule is being used in our daily life. Consider a simple random walk on a number line where a particle starts at a position 0 and moves either one step left or one step right with equal probability at each time step. So starting position, we all know that particle begins at position 0, and the step 1, the particle moves either left or right with 50% chance, and the step 2, the particle's next move depends only on its current position, not on the previous step. This is Markov's rule in action. Using Markov's rule, we can calculate the probability of particle being at any position after n steps. This allows us to model and predict the behavior of random walk over time. Fundamentals of Markov's chain states. Markov chains are specific type of Markov processes with a finite number of states. These states represent the possible conditions or configuration the system can be in. The next one is transitions. Transition between states occur based on probabilities defining the likelihood of moving from one state to another. These probabilities are represented in transition matrices. Time steps. Markov chains progress through discrete time steps where the system state is evaluated at a specific point in time. This allows us to model the system's evolution over time. Transition matrices and stationary distributions. Transition matrix. This matrix shows the probabilities of moving between states in a Markov chain. Each cell represents the probability of transitioning from one state to another. Stationary distribution. This graph illustrates the long-term probabilities of being in each state. It shows how the system settles into a steady state over time. Relationship and meaning. The stationary distribution is derived from the transition matrix. It represents the equilibrium state of the Markov's chain, where the probabilities of being in each state remain constant. The next thing is ergodicity and steady state behavior. Ergodic Markov chain reach a steady state over time, meaning the long-term probability of being in each state stabilizes regardless of the initial state. Steady state. In steady state, the system exhibits a predictable pattern and the stationary distribution accurately reflects the long-term probabilities of each state. Applications. Ergodicity is essential for many applications of Markov's analysis as it allows us to make long-term predictions and understand the system's equilibrium behavior. Some of the applications of Markov's analysis. The first one is weather forecasting. Markov's chain effectively model and predict weather patterns, considering factors like temperature, precipitation, and atmospheric pressure. Financial modeling. Widely used in finance, Markov's analysis models stock market trends, assert prices, credit risk, and investment strategies. Healthcare. In healthcare, Markov models study disease progression, treatment evaluation, and patient care. They stimulate disease trajectories and predict outcomes. The fourth application is network performance. Markov chain analyze and optimize network performance. The fifth application, customer behavior modeling. Markov model predict customer churn and optimize marketing. The sixth and last application is natural language processing. In NLP, Markov models handle language modeling. Now let us see how Markov's analysis is used in various fields. The first one is 20% growth. Markov model help forecast market growth by analyzing historical data and identifying pattern in price movements. $10 million revenue, predicting revenue streams for companies based on the customer behavior, market trends, and product demand. 10% risk. Assessing market risk by stimulating different scenarios and evaluating potential outcomes using Monte Carlo methods. Optimal decision making with Markov's processes. Dynamic programming. Markov decision processes allow for optimal decision making in systems with uncertain outcomes, finding the best policy to maximize reward over time. Reinforcement learning. Markov processes play a key role in reinforcement learning algorithms where agents learn optimal actions through trial and error. Applications. MDPs are used in various fields including robotics, resource allocation, and game theory. Limitations and assumptions of Markov's analysis. Memoryless assumption. The memoryless property, while simplifying analysis, may not always reflect reality. The past can sometimes influence the future. Stationarity. The assumption of stationary transition probabilities might not hold in dynamic environments where the system's behavior changes over time. Data availability. Accurate and sufficient historical data are crucial for building and validating Markov's model. Limited data can lead to unreliable results. Finally, the conclusion and future direction. Markov's analysis provide a powerful framework for understanding and modeling stochastic processes with a wide-ranging applications across diverse fields. Future direction include developing more sophisticated models, integrating machine learning, and exploring applications in areas like quantum computing and complex networks. Thank you all for watching my video.